Hi everyone, I see that I've already accumulated quite a few comments requesting a video about ether. But which one are you talking about? The simple ether or the complex ether? Or maybe the mythical one that Mendeleev talked about, mentioning it as an undiscovered new element? Or perhaps ether is some kind of extremely volatile substance? Well, let's figure it out. In fact, the word ether originated long ago, back in ancient Greece, when the scholars of that time tried to explain what the cosmos was made of, and they decided that it was filled with a higher substance called ether. This belief persisted all the way up to the 19th century. In the 19th century, scientists of that era tried to explain the propagation of forces like magnetism, light waves, and electricity by the presence of some kind of weightless fluid, a sort of ether that fills everything around us. Even Mendeleev believed that ether was some unknown ultralight element, 1,000,000 times lighter than hydrogen, which fills the vacuum. But everything changed when Albert Einstein introduced his theory in 1905, relativity, in which many mechanistic concepts like ether simply became unnecessary. However, for several more decades, many scientists tried to use the concept of ether in their research, but ultimately failed, as it turned out that ether simply does not exist. Well, I think we've now dealt with the outdated and already pseudoscientific theory of ether. Now we can finally take a look at which substances are the most volatile, and where various organic ethers rank among them. Let's begin, I think, with the chemical elements first, and then see just how volatile they can be. If you look at the table of boiling points for different chemical elements, you can notice that the lightest gas, hydrogen, is actually not the most volatile substance because its boiling point in Kelvin is 5 times higher than that of light helium. This is all because helium is a noble gas and has a filled electron shell. Its molecules interact with each other very weakly with one another. Because of this, liquid helium boils at a record low temperature of -269 degrees Celsius. In fact, liquid helium can be called the coldest liquid substance on Earth. Interestingly, when liquid helium evaporates from a dewar due to its extreme lightness, it rises up and resembles a swirling vapor more than a typical cold gas. In a transparent dewar, liquid helium behaves quite strangely, since it has the lowest density of all known liquids. Its density is 8 times lower than that of water, which makes it resemble a gas rather than something liquid. I think if scientists from 200 years ago had seen this, they would have definitely considered it to be that very mythical ether. Nevertheless, after helium, the next element at boiling temperature is hydrogen, which makes up about 75% of the total mass of the universe, while another 23% is helium. So, we are made up mostly of the remaining 2% of elements, which isn't all that much. By the way, hydrogen would also fit the old description of ether. After all, it is constantly escaping from our planet, being the lightest gas on Earth. About 3 kilograms of hydrogen escape from our planet every second. So this gas is practically the rarest on our planet. By comparison, there is 10 times more helium. Next in terms of volatility is neon, which exists in liquid form. I have hardly seen it anywhere, not even on YouTube. Apparently, to liquefy it, you need liquid helium, which is quite expensive. Nevertheless, this gas can be easily found at low pressure, for example in these ampules sold on the internet. If you bring such an ampule close to a Tesla coil, a bright orange plasma will appear inside, illuminating everything around with a beautiful warm light. And since orange light can be seen from quite a distance, neon was often used in bright advertising signs, attracting customers with its mesmerizing glow. After neon comes nitrogen, which everyone is familiar with. It is the most abundant gaseous substance on our planet. Because of this, buying this gas in liquid form is quite easy, and you can conduct various experiments with it, of which I have done quite a few in my life. With a boiling point 51 degrees higher than that of neon, nitrogen is not as volatile. And besides, its molecular mass is almost the same as that of air. Because of this, especially at low temperatures, this gas, after evaporating, just spreads along the ground and can be used for fire suppression. Moreover, because of its heaviness compared to, say, helium, nitrogen hardly escapes from our planet into outer space. On the contrary, it actually participates in the terrestrial nitrogen cycle. After nitrogen, in terms of boiling point, it ranks among the top. However, obtaining it in pure form is incredibly difficult. Only a few laboratories in the world can boast of having this gas. In Estonia, for example, there simply aren't any. So with your permission, I'll skip this gas. Next, in terms of boiling point and essentially volatility, comes argon. This gas is often used to create an inert atmosphere inside laboratory glassware. For example, for distilling substances that are sensitive to moisture or oxygen. To demonstrate the properties of liquid argon, we decided to initially freeze it using liquid nitrogen, since argon's boiling and melting points are very close to one another. Over a period of time, a small amount of solid argon formed within the test tube, which we then carefully placed onto black paper. Interestingly, this occurs because argon's boiling point is only 4 degrees higher than its melting point. The piece of solid argon simply disappeared in a matter of seconds, quickly melting and evaporating. To obtain the next gas in liquid form, you need very little. To do this, I poured a little liquid nitrogen into a titanium pot, and because of titanium's low thermal conductivity, liquid air began to condense on the pot, containing a higher percentage of oxygen than regular air. This is all because the boiling point of oxygen is already 14 degrees higher than that of liquid nitrogen. The resulting liquid air, which consists mainly of liquid oxygen, is strongly attracted to a magnet, since oxygen in its liquid form has paramagnetic properties. If you pour this liquid air into a glass, after some time the liquid nitrogen will evaporate first, leaving behind almost pure oxygen. And if you dip something flammable into it, it will turn into real rocket fuel. And that's not surprising because to this day, nothing is better than liquid oxygen. No one has yet invented a cheaper or safer oxidizer. For space rockets capable of overcoming Earth's gravity and delivering a payload into Earth's orbit. Or even farther. Next, in terms of volatility or boiling point, come the noble gases, krypton, xenon, and the radioactive gas radon. And it's interesting how sharply the boiling point drops among these gases. Speaking of krypton, this noble gas is not particularly remarkable. It can also form plasma, and if you freeze an ampule filled with this gas in liquid nitrogen, you can see a bit of solid krypton. But xenon in this regard is much more interesting. This is because, in addition to forming plasma and emitting light very close to the solar spectrum, xenon also behaves very unusually under high pressure, as in this ampule for example. Here xenon is under high pressure, about 80 atmospheres, and at room temperature it is a supercritical fluid. A supercritical fluid, which looks like something transparent. However, if you drop a little butane onto the ampule, it will evaporate and easily cool the ampule with xenon. This turns the xenon from a supercritical state into a liquid. But over time, the xenon gradually begins to warm up again, returning to its original supercritical state. It all looks quite unusual. Next in terms of volatility is chlorine, which, like all the previous substances, is a fairly toxic gas with a yellowish tint under normal conditions. Its boiling point is about -35 degrees. However, under high pressure, it can be turned into a liquid, just like many other substances. Here in this ampule, the pressure is about 25 atmospheres, which allows us to see the true color of liquid chlorine. After chlorine, all other chemical elements are already liquids or solids at room temperature, but they still have some volatility. In other words, they have a saturated vapor pressure. But to make it clearer, let's look at the example of bromine. If you pour a little bromine into a test tube, you can immediately see that, in addition to the liquid, the container is also filled with its brown-colored vapors. This happens because any liquid evaporates to some extent until it saturates the air above it. If you seal the test tube, you get a closed system, and the bromine vapors inside the tube become saturated. There will be nowhere else for the bromine to evaporate, and as a result, the pressure in the flask will increase slightly. The difference between the initial pressure and the pressure after evaporation is the value of the substance's saturated vapor pressure. In other words, how much vapor there is. The vapor of any substance can dissolve in a certain amount of air in a closed system. If you open the test tube, the entire atmosphere of our planet becomes the system. Therefore, by knowing the saturated vapor pressure of a substance, you can understand how easily a liquid evaporates, and accordingly, how volatile the substance will be. Bromine, by the way, evaporates 10 times faster than water, and its vapors are also quite toxic, so it's best not to mess around with this dangerous liquid. After bromine, the next non-radioactive element in the table is iodine, which, despite being solid at room temperature, is still quite volatile. All you have to do is leave a crystal of iodine in a closed container. In just a couple of days it will easily become stained brown from iodine vapor. This happens because iodine sublimates at room temperature. That is, it transitions directly from a solid to a gaseous state. However, to make this element evaporate more effectively, it's better to heat it to 180 degrees simply by placing it on a hot surface. More precisely, on a heat-resistant surface heated to 180 degrees. In this case, iodine first melts and then begins to evaporate, releasing beautiful violet vapors. Although the boiling point of this element is not listed in the table, the next most volatile element is phosphorus, which I can't help but mention, since in one of its modifications it practically doesn't melt at all. To demonstrate this effect, I first took a bit of red phosphorus, which over time in storage had absorbed a lot of moisture and partially turned into a mixture of polyphosphoric acids. To purify it, I dissolved it in water and filtered it, additionally rinsing the filter with distilled water. After drying, the phosphorus looks much more presentable. To try to evaporate the phosphorus, I placed a small amount of it into a bent test tube, one end of which was sealed with a water valve to prevent air from entering the tube. Now I heat the phosphorus in the test tube with a gas burner, and what do we see? It doesn't melt at all, but immediately starts to boil, almost as if in its dry form, producing yellow vapors of what is now white phosphorus. Yes, this is exactly what is strange about this element. It transitions from a solid state directly to a gaseous one at atmospheric pressure, and even changes its allotropic modification in the process. But freshly obtained white phosphorus can boil, so it can easily be distilled into the cooler parts of the flask. At the end, I heated the cold part of the flask with water to melt the small amount of white phosphorus obtained and collect it at the bottom of the jar. And by the way, white phosphorus is very toxic and dangerous, so do not try to repeat these experiments. And it is dangerous because even if you place a small piece of it on a cold surface in a cold room, it can stay there for quite a long time. And in the dark it even glows due to its reaction with the oxygen in the air. But as soon as you touch it, with something warm, for example a spoon, this happens. By the way, such a flame is almost impossible to extinguish with water, and white phosphorus itself can even burn on skin. That is precisely why it is now used in banned munitions to set everything around on fire. We've dealt with volatile elements. But what about the most volatile substances and those very same ethers? In fact, there are more than 1,000 substances that evaporate easily. But I'll show you some of the most common and interesting ones. Let's start with a substance called Trimethyl borate, which is a simple ether of boric acid and methanol. It's quite easy to obtain. All you need to do is mix a little methanol, boric acid, and concentrated sulfuric acid. Then heat the mixture and distill it. The resulting ether is collected in some kind of container. In this case, I distilled it and condensed it in a test tube placed in a beaker with water and ice. But still, this ether came out with some impurities, since it had a dark color. So for the demonstration, I decided to buy pure trimethyl borate and show you its unusual properties. The first thing that caught my eye was the special stopper, which allows you to draw the substance with a syringe. This is because trimethyl borate can react with moisture from the air, but I decided to remove the stopper and draw the substance in a way that was convenient for me. A distinctive property of trimethyl borate is that in addition to being volatile, it also burns very well, producing a beautiful bright green flame due to the boron atoms. Somewhere I also heard the myth that trimethyl borate has a completely cold flame, maybe because of the formation of boric acid? Let's check that. Yes, strangely enough, when I brought a piece of paper close to the burning boric acid ether, it caught fire, just as it should have. So, another myth about the cold flame has been debunked. There is also a rather volatile substance called chloroform. Although many people know this liquid as a weapon used by bad guys, in reality it doesn't work nearly as quickly as shown in some movies. And yes indeed, because of chloroform's high volatility and its sedative effect. This substance was used since the late 19th century as an inhalation anesthetic, where the patient would inhale chloroform vapors at a concentration of about 1% for several minutes. If the concentration was accidentally exceeded, a person could fall asleep and never wake up. Additionally, side effects included liver and kidney damage, as well as severe nausea. Plus, the minimum time it takes to fall asleep from chloroform is about 5 minutes. So, using it to knock out passers-by is more of a myth than reality. When chloroform is stored in air, a toxic gas is also formed. Phosgene, so old chloroform, should only be opened under a fume hood. Due to the high volatility of this substance, chloroform vapors quickly fill the glass, which can be tested by lowering a burning piece of paper into it. Like many halogenated compounds, chloroform does not support combustion, as can be seen by the extinguishing paper. Nevertheless, aside from its toxicity and volatility, chloroform is also an excellent solvent. For example, iodine dissolves well in it, coloring the solution a bright violet. Interestingly, if you pour water into a test tube, it will stay on top since chloroform is heavier than water. And the alcoholic solution of iodine will float even higher, as it is the lightest of all the liquids in the test tube. But that's not all. An even more volatile substance is an unusual liquid called carbon disulfide. And the first thing that hit me after opening this bottle was the foul stench of rotten meat. Although according to reference data, carbon disulfide is supposed to have a sweetish odor. It's all because in humid air, carbon disulfide hydrolyzes and oxidizes very quickly, forming several sulfur-containing compounds. For example, hydrogen sulfide, methyl mercaptan, and carbon oxysulfide. When ignited, carbon disulfide burns with a very bright blue flame and produces a large amount of smoke made up of sulfur dioxide. In addition to its high toxicity and volatility, carbon disulfide is also an excellent solvent, for example for sulfur, as well as for white phosphorus, which I synthesized earlier. Interestingly, in such a small amount of carbon disulfide, I managed to dissolve almost half a gram of white, or more accurately, yellow, phosphorus, since my homemade white phosphorus contained impurities of red phosphorus. To test just how volatile carbon disulfide is, I poured a bit of the resulting solution onto filter paper and started to wait. As you can see, the carbon disulfide began to evaporate rather quickly, leaving behind finely dispersed white phosphorus, which, after the solvent had completely evaporated, immediately ignited in air. It's also interesting that after the phosphorus burned, the paper itself did not continue to burn. This is most likely due to the formation of phosphoric acid, which acts as a fire retardant, just like potassium dihydrogen phosphate, for example, which is used to soak matches so they don't continue to smolder after burning. And now, the most volatile substance that is a liquid at room temperature is diethyl ether. It's quite easy to obtain, you just need to mix. Pure ethyl alcohol is mixed with sulfuric acid, then heated to 140 degrees but no higher, because at higher temperatures a flammable gas can form. Ethylene. The resulting diethyl ether gradually distills off at just 38 degrees Celsius. So you have to carefully cool down its rising vapors quickly enough for the volatile substance to condense before it escapes into the surrounding atmosphere. In the end, I managed to obtain a significant quantity of pure diethyl ether, which is a light, mobile liquid with a distinctive and pleasantly sweetish aroma. Yes, I still remember. I remember how, in the university organic chemistry lab, there was always a faint smell of diethyl ether, since students often produced it and then stored it in a sealed bottle. But it was so volatile that even in a well-sealed container it managed to saturate the air with its scent. If you spill a little diethyl ether even at some distance from a burning candle, even in a cool room the ether will quickly evaporate, and its vapors will ignite, sometimes even better than gasoline vapors. If you drop a little ether on your hand, it will also evaporate in just a few seconds. Interestingly, like chloroform, diethyl ether also has sedative properties. That's why, more than 100 years ago, it was used in anesthesia, and even as a substitute for ethyl alcohol. But just like chloroform, diethyl ether turned out to have many side effects on health, which led to its abandonment. And since the 1950s, more modern halogenated derivatives have been used for anesthesia. But in fact, diethyl ether is so volatile, what can you make from it? A real freezer that works without electricity if you evaporate it thoroughly. To conduct this experiment, I poured a little diethyl ether into a plastic container and simply started blowing on it with a regular hairdryer. On the thermal camera, you can clearly see how quickly the temperature of the ether began to drop as it evaporated. After a while, it even dropped below zero. Because of this, tiny ice crystals even started floating in the ether, which got there from the humid air. And after the liquid evaporated, there was just a clump of some kind of snow ice left. So yes, diethyl ether can be called one of the most volatile substances, if not the most volatile. Well, I think after watching this video, you now know what ethers are and which substances are the most volatile on our planet. And if you enjoyed this video, as always, don't forget to give it a like and subscribe to the channel to learn even more new and interesting things.